Welcome. In this lecture in linear data analysis, which has multiple sessions, we'll explore kernel PCA. Kernel PCA is a way of doing principal components analysis with the gram matrix of a data matrix. The main concepts for this lecture are we're going to avoid directly embedding vectors by using the gram matrix. This will let us calculate the dot products of the embeddings without actually doing the embedding. And we'll go through a derivation of kernel PCA, and then we'll go through the algorithm. One problem that we can keep in mind as we go through this lecture is how can we separate data that are nonlinear? What we can do, for example, with our data here is this is class +1 are the cyan plus marks, and class -1 are the red circles. These are visually separable, but they're not linearly separable. We can embed these in higher dimensions using in this case, quadratic kernel, and when we do this embedding into 3D, we can see that these data are now linearly separable. We can separate this view with a two-dimensional line, and in 3 dimensions, that would be a plane. So what we were doing was we were embedding these in a higher dimension, and that was mapping our original data, which have n variables, into a higher dimensional space, and we can write this as an embedding function of observation, in this case u. And a simple use of PCA in higher dimensions would be we would take our zero mean matrix and we would embed that matrix, and then we would form the scatter matrix, which is the transpose of the embedded zero mean with the zero mean. And a question is, how can we avoid doing this? We can see immediately that this mapping of the zero mean data into an embedding, the result may not have the same statistical properties. It may not be zero mean. And if we do find that zero mean, it's no longer clear how to do this PCA, and in particular, how to interpret the results.